Bismillahirrahmanirrahim. Assalamualaikum and hello everyone. Welcome to Unit 9 of FAST 5043. My lecture today will be discussing risk characterizations. In this unit, you will learn about what is the risk characterizations, as well as calculating the risk from the data given. Let's explore what risk characterizations means. Risk characterizations begins by bringing together all the information from the earlier steps in a risk assessment. It then synthesizes this data into well-rounded conclusions, clear, informative, and actionable for decision makers. Essentially, it reflects the expert judgment of the risk assessor, and it tells us whether risk to human health or the environment actually exists or not. So, risk characterizations is the final integrative steps in understanding potential hazards and guiding smart decisions. Risk characterizations isn't just a conclusions. It's made up of key components that bring clarity to complex data. First, we have the risk estimate, a numerical or descriptive expressions of how likely and severe the risk is. Next, it identifies which groups are most at risk, such as children, the elderly, or immunocompromised people. This component discusses uncertainties and variability. How confident are we in the data, and where might it differ? Every risk assessment includes assumptions. This part clearly outlines them and their implications. Finally, we look at the nature of the effects, what kind of health issues could arise, and how severe they might be. Together, these 5 components ensure risk characterizations is true, transparent, and useful for protecting public health. Risk characterizations help us understand the potential health impacts of exposure. Let's explore the 2 main types, quantitative and qualitative. Quantitative risk characterizations uses numerical estimates. For example, cancer risk is expressed as probability, such as 1 in 1,100. For non-cancer risk, we use metrics like the hazard quotients or margin of exposure to quantify the potential harm. But what if we don't have enough data for numerical estimates? That's where qualitative methods come in. Qualitative risk characterizations uses descriptive categories. These are especially helpful when data is limited or uncertain. To summarize, quantitative methods give precise estimates, while qualitative methods provide descriptive assessment. Both are essential tools in risk analysis. Risk metrics help quantify the potential health impacts of chemical exposure. Let's look at 3 commonly used measures. First, the hazard quotient compares exposure to a reference dose. If HQ is less than 1, the risk is considered acceptable. If it's greater than 1, it may indicate a potential concern. Next is the margin of exposure, which is the ratio of the NOAEL to actual exposure. A higher MOE means lower risk. For cancer risk, we multiply the dose by the cancer slope factor. Acceptable risk levels typically range between 1 in a million to 1 in a 10,000. Together, these metrics allow us to assess both cancer and non-cancer health risks, helping inform regulatory and safety decisions. Risk characterizations often uses guidance and guideline values, which are established internationally by bodies such as WHO, USFDA, US EPA, the EU, and the Codex. Some values are based on threshold concept. This means that below a certain exposure level, harmful effects are unlikely. If the threshold is exceeded, the toxicological effects may occur. For some chemicals, there is no safe threshold. Even the smallest exposure may carry a theoretical risk. These are called non-threshold chemicals. In food safety, international organizations set maximum levels of contaminants to protect consumers. Here, we compare European Union Directive and Codex standards. The EU sets strict limits on toxic compounds like benzoapyrene and dioxins in vegetable and animal feeds. Codex, however, has no set limits for this yet. For heavy metals, the EU allows slightly higher arsenics and lead levels in animal feeds compared to vegetable oil, while Codex is stricter for vegetable oil at just 0.1 ppm. The EU also regulates mercury, fluorine, cadmium, nitrites, and aflatoxin B1 in animal feeds and vegetable oil, while Codex provides fewer specific values. The EU sets more detailed and often stricter limits for contaminants. A good risk characterization clearly explains results, assumptions, uncertainties, and interpretations while separating science from policy. 4 key principles guide this process. First, transparency. Every step, assumptions and decisions must be explicit so readers understand how outcomes are reached. Second, clarity. Risk assessment should be simple and free from obscurity, so both experts and non-experts can understand them. Third, consistency. Conclusion should align with policies, guidance, and scientific rationales. If they differ, reasons must be explained. Finally, reasonableness. Assessments should be based on sound judgment, common sense, and acceptable scientific standards. Together, transparency, clarity, consistency, and reasonableness form the foundation of strong and reliable risk characterizations. Let's start with the basic idea. The hazard quotient, or HQ, is essentially a simple ratio. It compares two things: the amount of a substance someone might be exposed to and the scientifically determined safe level for that substance. This tool was developed and is primarily used by the U.S. Environmental Protection Agency to manage risks from air toxics. However, the concept is so useful now is now applied to many other types of environmental pollutants. Now, the most important part is how to interpret the number. If the hazard quotient is less than or equal to 1, it means the exposure level is at or below the safe level. We can consider this a negligible hazard. It's a green light. If the HQ is greater than 1, it signals for attention. It tells us that the exposure has exceeded the safe reference concentrations. It's crucial to understand that this is not a direct measure of probability that harm will occur. It's simply a flag saying we are above the recommended safety limits and we need to look closer. So, to recap, an HQ of 1 or below means we are in the clear, and HQ above 1 means we cross a safety threshold and need to investigate further. Now that we understand what the hazard quotient means, let's see how it's calculated. The formula itself is straightforward. It's the estimated daily intake divided by the tolerable daily intake. This is a well-established method as seen in protocols like Omar et al. 2019. First, let's look at the denominator, the TDI or ADI. This is the safe threshold we discussed. It's a fixed value that we don't calculate ourselves. Instead, we get it from authoritative, credible sources like these international health and environmental agencies. The numerator, the EDI, represents the actual exposure. This is where we input our specific local data. Unlike the TDI, we calculate this value using another formula that takes 3 pieces of information into account. So, what goes into the EDI? C is the concentration of the chemical we measured in the environment, like in fish. Consumptions is how much of that fish is a person typically eats. BW is the average body weight of the populations we're studying. By multiplying the concentration by consumptions, we get the total intake, and dividing by both by body weights gives us the intake for kilogram of body weights, the estimated daily intake. To summarize the entire process, we take our three local measurements: concentrations, consumptions, and body weight to calculate the EDI. We then take the internationally set TDI value. Finally, we divided the EDI by the TDI to get our final hazard quotients, which tell us the level of risk. Moving from human health to ecological health, we use the risk quotients or RQ method. This is a well-established approach used by numerous researchers to assess the risk pollutants posed to aquatic environments. The result of the RQ calculations is interpreted using a standard classifications. For example, as defined by Hernando and others, an RQ less than 0.01 indicates an insignificant risk, while a value greater than 1 signals a high risk to ecosystems. The RQ is derived from a simple but powerful ratio. It compares the concentrations of pollutants in the environments, either measured or predicted, to safe threshold known as the predicted no-effect concentrations. But where does the PNEC value come from? It is itself a calculated value. We take toxicity data like the LC50, which is the concentrations lethal to 50% of test organisms, and divide it by an assessment factor. This factor is crucial. It counts for uncertainties when lab data is extrapolated to a complex real-world ecosystems. So, the complete process looks like this. We start with toxicity data to calculate a safe level, PNEC. We then measure or predict the actual concentrations in the environment, MEC or PEC. We divide this to get the risk quotients. Finally, we compare the RQ to the classification scales to determine the level of ecological risk. This provides a clear quantitative assessment. Let's put the theory into practice with a concrete example. We'll assess the risk for factory workers exposed to benzene, a common but hazardous solvent. Our scenario involves adult workers with long-term daily exposure, primarily through breathing it in. To quantify the exposure, we need three pieces of data. First, we measure the concentrations of benzene in the air the workers breathe, 0.5 parts per million. Second, we estimate how much air a worker inhales daily, 20 cubic meters. Third, we use a standard average body weight of 70 kilograms. Now, we apply the formula for estimated daily dose. We simply plug our measured values into the equations: concentrations times inhalation rates divided by body weight. Now, for the calculations, 0.5 times 20 equals 10. Dividing 10 by 70 gives us approximately 0.143. So the estimated daily dose for these workers is 0.143 milligrams per benzene per kilogram of body weight per day. We have our results, 0.143 milligram per kilogram per day. But what does this number means? Is it safe? On the next slides, we will compare this dose to a known safe level or reference dose to calculate the hazard quotients and finally characterize the risks. Before we can understand the risks, we must understand the hazards. Benzene is not just any chemical, it's a confirmed human carcinogen. It also causes serious non-cancer effects like bone marrow damage. Scientists have determined specific toxicity levels called point of departure for these effects. To create a safe level, we take the LOAEL, the lowest dose that should harm, and divided it by uncertainty factors. These factors account for scientific gaps. A factor of 1000 is common, giving us a reference dose of 0.0013 milligram per kilogram per day. This is our safety threshold. Now, the critical moment. We compare the workers' actual exposure, EDD, to the safe level RFD by calculating the hazard quotients. We divide 0.143 by 0.0013. The result is not just slightly over 1, it is 110. The interpretation is stark and alarming. An HQ of 110 means the worker's exposure is 110 times higher than the deemed safe levels. This is not a minor accident. It indicates a significant risk of blood disorders. The conclusion is clear and urgent. Immediate protective measures are absolutely necessary to reduce exposure. Now that we have quantified the significant risk, what can be done? Risk management follows a hierarchy of controls, aiming for the most effective solution first, like eliminating the hazards, before relying on less reliable methods like personal protective equipment. Based on this hierarchy, here are specific recommendations. First, investigate if benzene can be substituted with safer alternative. If not, engineering controls like local exhaust ventilations are essential to remove the contaminant at the source. Administratively, limit the time workers spend in high exposure areas. PPE, such as respirators, is necessary but should be last line of defense. Ongoing monitoring of both the air and the workers' health is crucial. And finally, comprehensive training ensures everyone understands the risks and procedures. How do we communicate this finding to decision makers and workers? This message must be clear, concise, and actionable. A risk professional communications statement will be: benzene exposure poses unacceptable risk. This statement clearly summarizes the problem, the severity, and the required action without causing unnecessary panic. This concludes our risk characterization example. We started with assessment, calculating a hazard quotient that revealed an acceptable risk. We then moved to management, outlining a hierarchy of solutions. Finally, we crafted a clear communication statement. This three-step process, assess, manage, communicate, is the cornerstones of effective risk assessment. That is all for Unit 9. Thank you for listening. Until we meet again in the next unit.